Look at how teams document software architecture. They crowd into a room, covering whiteboards in a chaotic, ad hoc web of squares, cylinders, and lines. This approach creates dangerous ambiguity. You end up with unlabeled arrows and mixed abstractions on the same board. For instance, someone will sketch out a stick figure representing a high-level user and place it directly next to a specific low-level database table. On the opposite end is traditional UML. While it provides strict rules, teams have abandoned it because it requires mapping microscopic class structures by hand. Failing to establish a shared model creates a gap between business intent and engineering execution, leaving the team lost. This table maps out the core issue. Different people require entirely different scopes of information. A product manager needs the broad systemic flow. A back-end developer needs the exact API endpoints and database schemas to write their code. To bridge this divide, software architect Simon Brown created the C4 framework. The framework treats software architecture exactly like a digital map. Just like Google Maps, you start with a wide view of a continent and then seamlessly zoom down to a city grid, a neighborhood, and eventually a single building. C4 achieves this without forcing a rigid visual syntax. It relies entirely on a common set of abstractions rather than demanding specific shapes. Standard boxes and lines work perfectly, as long as the team uses a clear diagram key. Standardizing the abstraction levels aligns an entire organization around a shared architectural vocabulary. The highest abstraction in this framework is Level 1, System Context. This context diagram places a core software system within its broader environment. It defines its users and external dependencies. We see specific data boundaries, information flowing to the personal banking customer, and connections bridging to the mainframe banking system. Because it defines the complete scope of the project, this top layer acts as a traceability tool, mapping system boundaries directly back to high-level business drivers. Executives and product managers can verify the project's direction immediately without getting bogged down by technical details. From there, we move down to Level 2 by zooming directly inside that central system boundary. This diagram shows the container level. Here, a container doesn't just mean Docker. It represents any runnable technology block that executes code or stores data. Looking inside the boundary line, we see the deployable units making up the system: a web application, a single-page application, a mobile app, and the central API. Between these blocks, the diagram maps out technology stack choices and communication protocols, noting exactly where JSON over HTTPS or JDBC connections are required. Defining these blocks maps to non-functional requirements, forcing decisions about scalability, security, and hosting. This makes Level 2 the critical meeting point for software architects and IT operations. They can finalize the deployment boundaries together before the development team writes a single line of code. Once the containers are defined, we zoom in to one specific block to reach Level 3. This diagram shows the component level, decomposing the single API application container into internal modules. We see how the application splits into specialized controllers, isolating the routing and business logic for signing in, resetting passwords, and viewing account summaries. Below those, the diagram tracks how those top-level controllers collaborate with underlying service components, like the security component and the mainframe facade, to actually execute those tasks. This structural breakdown provides functional traceability. Each component maps directly to a specific user requirement or feature. The target audience here is the software developers. They use this map to understand the exact internal structure before implementing new features. Applying this level of component rigor ensures that when an engineer finally makes an individual code change, it aligns perfectly with the intended overarching architecture. The final step is Level 4, zooming into the microscopic implementation details of the system. This code-level diagram shows a standard UML class structure. Hand-drawing these individual exceptions, facades, and interfaces is incredibly inefficient, making Level 4 optional for most teams. When a team does require this code-level view, they generate it dynamically via static analysis or reverse engineering tools pointed directly at the existing codebase. This diagram captures the complete layout. When we pull back and look at all 4 layers working together, the value of the framework becomes clear. This unbroken chain of intent ensures every microscopic code decision traces directly back to the boardroom's original business drivers. Many architects blame messy documentation on lacking strict UML rules or better tools. The real issue is the process. Diagramming draws a static picture. When the system changes, it becomes obsolete. This creates documentation drift. Developers update code, but the drawing stays the same. With modeling, you build a connected representation where every layer is intrinsically linked. Documentation drift causes engineers to ignore the architecture. Once the map fails to reflect reality, organizational trust collapses. Shifting from a diagramming mindset to a modeling mindset ensures that when one element changes, the updates propagate everywhere. It is the only way to build a reliable single source of truth. Modern software tooling turns the C4 philosophy into an automated reality using interactive platforms and diagrams as code. This shows the ICE panel workspace, displaying an e-commerce architecture as a connected model. Architects author the context diagram first, seamlessly refining it into containers. Interactive models document flows step by step, turning static images into living documentation. When you combine these connected C4 models with practices like domain-driven design, you can explicitly map specific software containers directly to the engineering teams responsible for maintaining them. No matter how well an architecture is planned, diagrams only provide value if they are ruthlessly maintained and synchronized with operational reality. The C4 model provides a consistent architectural vocabulary. Executed as a living model, it bridges the gap between high-level executive intent and low-level engineering execution.